Welcome. This week I realized that some of the things I'm working on has close relations with topics Henry McKean was working on. He passed away in April of this year, and he worked on partial differential equations, especially equations which also have relations with stochastic processes, like with diffusion processes or processes appearing in finance, nonlinear systems, which are then closer related also with integrable systems like the Korteweg-de Vries equation, which have relations with Schrödinger operators. And that's another theme here, inverse spectral theory of one-dimensional Schrödinger operators. It's an interesting topic, like when we look at the Sturm-Liouville problem. So the spectrum is in general in infinitely many bands, but he was investigating first, for example, what happens if you have finitely many gaps, and then the story is similar than in the discrete case, where you have just also finitely many intervals, and then there are hyperelliptic curves, there is algebraic geometry. So it's no accident that different topics here come together, like algebraic geometry and partial differential equation probability theory. One can also see from the students of McKean. He was a student of Feller, probabilist, and his students, some of them went into probability, some into discrete math, like Victor Moll, who was once here. Drubowitz, one of his students, was my Calc 3 teacher. He was a very inspiring teacher. He was just arrived at ETH in '83 and gave this introduction, complex analysis. Complex analysis was analysis 3, and harmonic analysis, analysis 4. And I even have a picture of him. I had at that time this camera. Actually, I have still, this camera, the same camera. I had it with me as a student or in military, and so I could make spy photos. I have a picture of him teaching, and he was actually also talking about Sturm-Liouville problems, for example, or all kind of topics which usually are not covered. So it was a very inspiring thing. When I finished my PhD, I just met him, and he asked what I'm doing, and I said I'm working on discrete Schrödinger operators, like I was actually working on Jacobi matrices, spectral theory of Jacobi and integrable system. And he said, and with a typical joke, yeah, that was a girlfriend of mine, now you have my girlfriend. So he was at that time already working on other things like Fermi stuff and quantum field theory, quite heavy analysis. All these classical topics which, McKean was working on also, appears into discrete. And you see that I just saw when I worked on a paper in spectral theory, which recently got published even, so I bothered even to submit it, and it's really a nice result, I think, but it's related to a story of McKean, because he was advising Anderson and Morley to look at the, maybe one form Laplacian instead of just the zero form Laplacian on a graph. And on a graph or simplicity complex, you can look at all the form Laplacian. It's a wonderful thing. And I looked once, kind of more than 10 years ago, at this McKean Singer symmetry, which is also a theme of McKean, right? So you have this beautiful story in Riemannian geometry. So you have this beautiful Laplacian. It cannot be simpler, right? You have this Laplacian, this Hodge Laplacian, and which gives you the Betti numbers. The cohomology are the harmonic forms, and you have this also Atiyah Singer story here, the index, and so no accident that Singer, you know, Singer, Isidore Singer, he was also here a couple of times. So quite a few of the relations of McKean have been here. Stroke was teaching here once, and of course Singer was kind of in events visiting. What I was working on this week was gain more understanding about this isospectral deformation of the Dirac matrix of a discrete geometry. This also works for in Riemannian geometry. But I looked at that 11 years ago, and I first of all just noticed that this is a nice symmetry, because what you can do is you can deform this Dirac operator is no more just of the form d plus d star plus d plus d star plus m, where m is a diagonal term, but it's isospectral, and so it would be interesting to know what is this isospectral set. That's really a McKean theme, right? What is the isospectral set? What is the inverse spectral theory? How can you reconstruct this D from the spectrum and possibly from an auxiliary spectrum? So I believe, that's not confirmed, I believe you can actually, you know, take away one of the rows and columns of the Dirac matrix, you get the auxiliary spectrum, and then look at these and these auxiliary spectra, and maybe you need more than one, and this spectrum itself should actually be able to determine the Dirac matrix, and so the geometry completely. That would be extremely nice. And also what would be nice is to understand the isospectral set. That's expected to be here also the case. That's not confirmed, but we expect that there is actually just a torus. This torus can be embedded in SON, where n is the number of elements in the simplicial complex. So n SON, that's then the kind of all the rotations which you have in this Hilbert space of all functions on G. And so these are orthogonal transformations, and this produces a curve in these orthogonal transformations. And it's like in a differential geometry of curves, what you have is a skew-symmetric matrix B, which is actually here also appearing. This skew-symmetric matrix B is, you can also describe it as a path of skew-symmetric matrices, which are kind of like the curvatures in differential geometry. So you can describe this deformation. There's an equivalent here, and also that's equivalent. So, I mean, this QR decomposition gives you dt. So it's kind of, there are two pictures. Both of them I have implemented in the computer, and then you get close to h of t is equal to d, but it's not quite the case. So what would be interesting to know what happens with these relations. The picture is kind of confirming that we have the number of different eigenvalues really matters for this isospectral set. So it's a torus which is kind of, you know, the dimension should be the number of gaps which you have in the spectrum, like in the classical case of, you know, this hyperelliptic curve story. So that would be kind of interesting to explore more. And but what is nice for me, I'm very happy about this QR story, because the Q's are, you know, just from QR decomposition, immediately you see that the Q's are of the same block trigonal form than the D, and then you take the derivative and you get the B, which is also block trigonal. And so this is really nice, because you can, without solving a differential equation, you can immediately get discrete time. You can immediately tell what happens at time t. You can just compute it via a QR decomposition, which is really kind of useful. It's also for me very satisfactory, because what happens, and that's also related to McKean's stories, right? If you look at the story from the point of view of, you know, as a physicist, like Feynman path integrals, which gives you the solution of the Schrödinger equation, what you can do is, here in the discrete, it's just a Taylor theorem, which gives you a sum over all possible paths interpretation of the solutions of the wave equation or heat equation or whatever. You are looking at differential equations which involve a finite matrix. So what happens is that if you look at the wave equation in the continuum, then this has finite propagation speed. The wave equation is discrete, doesn't have finite propagation speed. It actually kind of, when you start the wave at the point, it immediately matters what happens far away, because you look at the eigenfunctions. For example, the eigenfunctions depend on the whole space and not only local. So it's kind of almost not visible because it's a very, very small effect if you're far away, but it's not quite true that the speed of information can travel only with finite speed, which you really want to have. But here it happens, and I'm very happy to see that. Kind of if you take here maybe 1 plus d, if this function, this can be any function, it's like an invertible function like 1 plus d, then you have finite propagation speed within the blocks. Also, if you have a point here and a point here, they don't immediately influence each other. So it needs a finite time until this point influences that point. And that was not clear here when you look at that. And I think in general it's not true if you take a general function here. So that's what I wanted to say today.